So there's another method that we can use to find volumes of revolution that don't involve a disk or a washer. So this is not covered in the BC Calculus curriculum, but it is something that you probably would have learned if you took Calc 2 in a college course, and I actually really like this method for finding volumes because I think it works really nicely for certain situations, and it's called the shell method. So we're still going to be revolving an area. So I have this shaded region in, and let's say that we're going to revolve this around the y-axis. So normally if we were doing a disc or a washer, if we were to draw a little rectangle that we were going to rotate, we would draw it perpendicular to the y-axis. So we would need to make this a dy integral. The way that the shell method works, and you can kind of think of this because there are two lines at the end of shell, right, which are the symbols for parallel, I'm going to still draw a vertical little rectangle here. So I'm going to imagine that I'm taking this little rectangle and I'm rotating it around the y-axis. And as this rectangle moves throughout the region, right, so as I rotate this, I'm just creating like a little shell. It's basically a little hollow cylinder that's very thin. So what you can kind of think about for the shell method is we're building volume the same way that a roll of paper towel has volumes, right? If you take one piece of paper towel off, right, one layer of the roll, right, it's really thin, it doesn't have much volume. But as you add more and more layers, as you keep winding those paper towels around the roll right on the inside, that little cardboard cylinder, right, you get a volume. That's the same way that the shell method works. You take this rectangle and you spin it around the axis of revolution and you create this little shell. So if I were to rotate this, right, I'm a certain distance away, right, I'm going to call that my radius. But when I rotate this, what I get is, I'm just going to draw it a little bigger. I'm going to ignore my really bad. Three-dimensional drawings. Right, we essentially get this little shell. So the solid part is the rectangle that we would have rotated. So, and you can think about like if you take a piece of like, if you were to be able to like just take a thin layer off of a paper towel roll by like just putting your hands on the sides and sliding it up and just sliding that piece off with like without having to worry about like tearing it off, right? You can tear this apart, right, and create a rectangle piece. So what we're really doing is we need to find the area of the rectangle that we just took a layer off of our paper towel roll, and as we add up all of the areas of these paper towel rolls, right, as we unroll the roll, right, we get the full volume. Seems like a weird analogy at this point, but I'm going to keep going with it. So anyway, right, the height of our rectangle is going to be the height of this piece of paper, right, this thin little rectangle that we get from our shell. And then if we think about how we're going to get the length of this rectangle, right, if you think about slicing a cylinder down the side, when you unroll it, this is really the circumference of that, which is equal to 2 pi r. And in this case, r is going to be a function of x, and I labeled that with a blue marker, so we'll label that with a blue marker. So for the volume with the shell method, is you take the integral from a to b, so in this case it would be a to b of 2 pi times your radius times your height, where r of x is the distance from the axis of revolution and your h of x function, or it can also be in terms of y, is the height of any sort of representative rectangle. So the key here is for shell method, the rectangles are parallel to your axis of revolution. So I'm just going to go through a couple of examples to show you why I like this so much. So the first thing I'm going to do, the first example we're going to do is if I take the region bounded by x equaling y cubed, y equaling 3, and x equaling 0, and I want to revolve that about the x-axis. Okay, so first we probably need a graph. Okay, so we have y equaling 3. Okay, so let's see, we got 1, 2, 3. Let's see, if y is 3, I need to go out to an x of 27, it looks like. I'm going to count by 3s here. Okay, so let's see, 0 cubed would be 0, 1 cubed would give me 1, 2 cubed would give me 8, which might put me here, 3 cubed would put me out at 27. Okay. There's my badly drawn graph, we're fine. So we got the line y equaling 3 here, so we got that. Okay, so our area that we are rotating is this area right here, and we are rotating about the x-axis. Okay, so I'm going to draw a little rectangle here. So we're going to draw it parallel to the axis of revolution. So here's my little rectangle. Right, and my height of my rectangle is just the distance out to the curve. So my height here in terms of y is going to be y cubed, because now my rectangle is falling along the y-axis, so that tells me I want to be in terms of y. And then my radius is also going to be in terms of y because I am horizontal, right? So my distance from the x-axis to wherever that rectangle is just the y-coordinate, right? Whatever the y-coordinate is, that's just the height the rectangle is above the axis of revolution in this case, which is the radius. So our volume is going to be 2 pi. We're just going to pull that to the front. And now we're in terms of y, so I'm going to go from 0 to 3. And then my radius is y times my height of y cubed. Right, so I'd get 2 pi times the integral from 0 to 3 of y to the 4th dy, and that's just 2 pi over 5 times y to the 5th from 0 to 3. The 0 would cancel out, and 3 to the 5th, I want to say, is 243. Yep, so we would get 243 times 2, so that's going to be 486 pi over 5. Okay, let's do another one. Let's do a little bit of a harder one, and I'm not seeing anything. Okay. You know what? We'll just make one up. So now let's talk about why I really love the shell method. So this problem is going to really show why I love the shell method. So we're going to do the area bounded by y equaling x squared minus 5x and y equals 0, and we're going to revolve this about the line. Let's go x equaling 8. Just making this up. Okay, so let's draw a little graph here. Okay, so I've got my axis of revolution at 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's draw our graph. So I'm going to have x-intercepts at 0 and 5. 1, 2, 3, 4, 5. If I plug in 1, I get 1 minus 5. So 1, 2, 3, 4, which matching point there. Okay, so if I do 2.5 squared minus 5 times 2.5, that's going to be my vertex at negative 6.25. So 1, 2, 3, 4, 5, 6. So we're about there. And then the line y equals 0 is just the x-axis. So we want to revolve this area along the line, around the line, x equaling 8. So now if we were using a disc or a washer, right, we would draw rectangles like this, and we would actually have to change this into a dy integral, which means that we would have to solve that first equation, that parabola for x, and in this case, we would have to complete the square in order to do that, and then we'd have to break it in both the positive and negative square root. It's a mess. But the shell method, super duper easy. I'm just going to draw a little rectangle here. So because I'm now going to be parallel to my axis of revolution, I don't need to change anything. So I'm still going to have a dx integral because I'm lying along the x-axis there. So now my height is just the distance of the curve, and I want to make sure it's positive. So my height is going to be that 0 line minus the parabola. Right, in this case, that's just going to turn into 5x minus x squared, just reversing it. And then the radius, now this is a little harder to think about. So our radius is the distance between my axis of revolution and wherever my rectangle is. So in this case, we got to think about it a little bit. So normally, like when we graph, like if I were to draw the distance from here to here, this is the x coordinate, right? If you're moving just from the origin to the right, that's your distance is just the x coordinate. And then if I were to go from here to here, right, this distance is 8. So my radius is then going to be my distance of 8 minus the x coordinate. It's just the difference between them. So now when I go to find my volume, I'm going to get my 2 pi on the outside. Now I will say the biggest error I see with students when they use shell method is they forget the 2 pi, or they try and square something because it's like a disc or a washer. You don't have to square anything here. So then my limits on my area would be from, that's not what I wanted to do. I go from 0 to 5 on the x-axis, so my limits of integration from 0 to 5. My radius is 8 minus x, and my height. Okay, so if I wanted to integrate this by hand, which I totally can, it's just going to take some time. I'm going to FOIL that out, so I'm going to get 40x minus 8x squared minus 5x plus x cubed. Now it's just going to be a lot of power rules. So I got 2 pi times, let's see, that's going to be 20x squared minus 8/3 x cubed minus 5/2 x squared. Probably should have combined those, but whatever. Plus 1/4 x to the 4th from 0 to 5. Go ahead and combine my like terms now, I guess. So that's going to be 35 over 2 x squared minus 8/3 x cubed plus 1/4 x to the 4th. Now all the zeros are going to cancel out that term, so I'm not going to worry about that. So 2 pi times, let's see, 35 times 25. 5, carry the 2, 15, 10. Okay, so that's 875 over 2 minus 125 times 3. 375 over 3. I was supposed to multiply it by 8, not by 3. I'm going to say that shouldn't reduce. There we go. Okay, so 0, carry the 4, 16. Okay, 1,000, that was easy. And then plus 5 to the 4th is 625 over 4. I guess we'll finish this out. I'm just going to leave the 2 pi out front. My least common denominator is going to be 12. This is getting really messy. Okay, so that's going to be 4,000 over 12. That one's pretty easy. Okay, that's going to be 875 times 6. So that's 30, 42, so 45, 48, so 52. And 625 times 3, that's 15, 7, okay, 1875. Okay, so let's see, plus 1875, that's 5, 12, 11, so 7 minus 4,000. Okay, so that's gonna be going to translate to 3125 pi over 6. Let's see, that's 7, 4. Okay, so it's not divisible by 3, so it's not reducible. Okay. And there we go.